Assalamualaikum. Hello everyone. CHENG324 process modeling and simulation, and this is where we have stopped last time for lecture number 4, at the end of lecture number 4. So today we are going to take lecture number 5. Okay, great. So this lecture number 5, we have stopped to say, well, we need to know how does temperature change with time so that we can calculate it. So where did we arrive to? We arrived, I think I'm going to use the black ones, just clearer. We have reached to this stage in which we were talking about a CSTR, and in this CSTR we were trying to know how does height change with time so that we can control the height not to overflow and not to empty. And we also wanted to control the concentration because we want to sell our product. So sell our product with specifications, and one of the main specifications is the concentration, and that is why we have identified very clearly how does concentration of A, B and C do change with time so that we can control them. And if we look at it, what else do we have? Yes, and this happens at a certain temperature. It happens at a certain temperature. So we want to control the temperature. So the next step, what we're trying to do here is to control the temperature. And to control the temperature, as we can recall, if you want to get the temperature, we can get that from the energy balance equations. And this is what we are going to do now in a moment. So how to start with the energy balance equations? I know sometimes you think of, oh my god, energy balance, that's a nightmare. Oh my god, what should I do? Forget about it. Don't feel like that. It shouldn't be like that. Just have the happy face. You should forget about having this scary face. So what do we want? We want to find how does temperatures do change with time. Talking about the energy balance equation from the law of conservation, what do we have? We have this equation that we're going to start with, dmu by dt. Well, it's not only u actually, it's like the whole energy, dme by dt is equal to the mass flow rate in with all of its energy in, plus minus the output, the mass flow rate out with all the energy outputs with it, plus if I added any heat within the system, plus if I have added some more to the system, and this work it just reflected to add heat to the system, or it was work done by the system, so there was some energy taken out from the system. So this is the main equation. This is the main equation that we have in this problem, and we are going to start from here. And solve our energy balance equation and try to get what? Try to get the dt by dt term. So that is our goal. We want to know how does the temperature change with time. So we are going to do this step by step, and doing it step by step, we're going to start now to do some kind of assumptions that will just reduce our problem easier and easier. We're going to the energy term. Well, I'll write that with blue as it's not a continuation. Oh my god, what was that? Something appearing here. Delete, please. Okay, good. I got rid of it. Then, so what do I have here is that energy. So energy is equal to, I'll increase that a little bit, I think better for your eyes. So energy is equal to the internal energy plus the kinetic energy plus the potential energy. Oh my god, we have all of these terms. Yes, we have all of these terms. But let's think of it. What is the comparison of these terms of kinetic energy in comparison to the internal energy? Well, if you think of a system again for the CSTR, if something hot, if hot water or whatever hot liquid gets in, definitely is going to add energy to the system. In other words, it's going to become hotter. It's going to become hotter, yes. Well, now you can tell me, does that height really add as much as what hot water can add to the energy? In other words, if the temperature was 50 degrees and the hot water was 100 degrees, that will definitely raise the temperature like from 50 to 75 or 78, whatever degrees. But does that height really affect as an energy, talking about the potential energy? Does it really add something? The answer is no, definitely not. Definitely not. Not even a 1 degree centigrade. It will not affect. So comparing of what a potential energy can add energy to what a real hot fluid would add to the energy to making this liquid hotter, definitely potential energy is negligible. Great, we got rid of the potential energy. Now what about the kinetic energy? Well, would you think that just making your process faster and faster and faster, I don't know how to draw faster, would that add 1 degree even to that system in comparison to a hot of water? Definitely not. So in that case, kinetic energy is also negligible in comparison to that internal energy, how hot it is. The internal energy, of course I understand I said how hot, and actually the internal energy is much more than that. It's not about how much does it really store that energy in that bonds that it has. It's even more than that. But we're not going to go to the details, but we say that internal energy definitely is going to be more than the potential and kinetic. So kinetic energy is out. So simply we're going to have only the internal energy in the term. Beautiful. I like this. I like having the U by itself sitting. So if we're going to write our equation again, it's going to go like that. dmu by dt is equal to the flow rate in with u in minus the flow rate out with u out plus q plus w. So that is the first part that you're trying to achieve here. Okay, so now let's talk about, of course I'm doing it step by step, and I'm doing it based on what I have solved before hundreds of times. So this is the key of what I'm trying to solve here. Maybe you would ask, why did you select now to work on the W term? It just came from experience. Okay, so you're going to do that later when you study this course. So now I'm going to work on the work term. The work term is energy, and definitely if you're talking about fluid flow, for any flow of fluid, definitely it has energy. Well, do you want to make sure about it? Very high energy on a bend of a pipe. What happens here? If it's weak, it could break that pipe. Another thing, we have a big car or fire extinguisher having fire, and this fire they're trying to put it off. So they put this big pump putting in water just to try to get rid of this whole heat that we have. So there's a fluid flow. There's a very high fluid flow. If you stand here, you cannot withstand this pressure that's coming to you and pushing you. It's high energy. So simply what we're trying to say here, that W definitely is this like a fluid flow, or they call it the PV work. PV work. And here we are talking about, of course, everything per time. Here is per time, per time, per time. So the PV work, instead of saying the PV, it will like be P into the volumetric flow rate. And here I'm talking about the input minus output. So it's going to be the Pn Fn minus the Pf. Okay, so this will be Pn Fn minus Pf. Okay, great. So let's continue the other term. So that was plus Q, that's the other term. And here it was MIUI minus MU. So what was MIUI? MI was, if you can recall, it's rho I Fi into UI minus rho F into U plus Q plus PIFI minus PF. Great. And that is equal to dmu by dt. Well, we just can see that we have a term that looks like there's a common factor here. Beautiful. And we have another term which also has a common factor here. And let's take a common factor, and now we're going to be like somehow waving around, naughty about how we do this thing here. It's all about being clever of how taking the common factors. Here we're going to take the additional common factor of rho I and of rho I, simply rho I, even though there's no rho I on the other term. And you're going to see what's going to happen here. So if you take rho I Fi as a common factor, that is definitely going to be Ui plus is going to be Ui plus Pi, and this Pi, because there's no rho I here, it will be divided by rho I. Oh, wow. So that will be divided by rho I, and this is why you find out there's something different here which is happening. Yes, it is different, and you're going to see it. And if you continue in the other terms, rho I, sorry, it's rho into F. So that is rho F. And similarly, U plus P over rho. And the rest of the term is what? After we got the two terms here, we are left with Q plus Q. So this is what we left with. Okay, what is Ui plus Pi over rho I? That looks strange, but maybe it will look better if I wrote it as Ui plus Pi into the specific volume. And by the way, all the terms that we have here is per mass. So all of the terms here are already per mass. This is per mass and so on, per mass. And why I'm saying that these are per mass, if you look at the units, here, this is like kilogram per second, and this is like energy per kilogram. So you cancel out the kilogram. So what do you have here is energy per second, and this is exactly what is here. So U is energy. U is energy per kilogram multiplied by kilogram, so that will be energy, and per second, which is by dt here. So these are all per mass. So here we have U plus PV. Beautiful. And that will be minus the other term, which will also look like rho F into U plus PV, the specific volume. And what makes it better is that we know that this term is equal to enthalpy. And I'll make it just capital H just to separate it from the one which looks like height. And here we have enthalpy. Enthalpy is a beautiful term. It just made our example much simpler. Rho Fi Hi minus rho F into H plus Q. What a beauty. How is our equation is just getting easier and easier. And what we have, dmu by dt is equal to rho I fi hi minus rho fh plus q. Don't worry about q. We are going to look at q in a moment. But that is as simple as the term that it looks like. This is the term that we do have here. It is as simple as you can see in this problem. Well, we want to go one step forward as well. We want to get the dt by d term. We still have it. We did not obtain the dt by dt term. So this is our goal. This is our goal. We still did not achieve it. We want to achieve it. Well, we are there. We will try to achieve it in a moment. So let's work on the left hand side, and then we are going to go to the q part. Looking at the left hand side of the term, here we have m and we have u. Okay. What I want to say is that you can start from here for exams. Start here for solving problems. Because most of the chemical engineering problems that we have for our systems, you can simply start from here. Because what else is we have taken as kinetic energy negligible and potential energy negligible is always applicable. And actually, if we have liquid systems and delta P is not very large, and usually this is the case that delta P is not very large, we can simply say that U is equal to H, enthalpy. Wow, what a beautiful term. Why it's equal to H? Because we know that U plus PV is equal to H. And we're just cancelling out this term because of the liquid system. You have pressure. Does pressure change volume? It does not change volume. And so talking about that term, we are simply cancelling out the term here, and we're having U is equal to H. And here's the system that we have, dmh by dt. Well, why to write it as m? We want to even simplify it more, just to shorten our problem here. We know that m is equal to rho into v. We already know this, so we just want to substitute that, and it will become easier for us to solve our problem. So let's continue. We say that this is equal to rho I fi hi minus rho fh plus q, and then we are going to say that density is constant, and we are going to have the volume with the height, sorry, not height, the enthalpy term is equal to rho I fi hi enthalpy minus rho fh plus q. Here we have a multiplication, and this multiplication we apply the product rule, so we can say that rho, which will be multiplied by v dh by dt plus h into dv by dt is equal to rho I fi hi minus rho f into h plus q. And if you recall that dv by dt is equal to, yes, I'm sure that you can remember that, is equal to fi minus f. I knew that you can remember that. I just heard it. Okay, so that will be rho into v dh by dt plus h into fi minus f. Beautiful. We just got rid of dv by dt, which is equal to rho I fi hi minus rho fh plus q. And very similarly, as we have done before, you can see that we can have a term here that can be cancelled out, and the term here that we cancelled out is rho fh. If you can see this, rho fh, and this is the fh with the rho. And then we can take a common factor, which is rho fi. This is rho fi into hi minus h. So to do it in another step, this will be, So this will be rho v dH by dt is equal to rho I Fi into Hi minus H plus Q. Wow, that is really a very simple equation. And H, and now you can remember from heat transfer that H is equal to Cp into T minus T reference. And it could be more complicated, yeah, but that, no, it's not more complicated. It's that H is equal to Cp into T minus T reference. And if we substitute that, considering that could be more complicated if Cp is changing. Now we're just considering that Cp is constant. Cp is constant. So this will be like rho into V. Okay, where did my equation go? Sorry. So that will be rho into V into Cp d. Of course, I took Cp out of the derivative term that because it's constant, into dt minus d reference by dt is equal to rho I Fi. We will substitute here Cpi into Ti minus T reference minus Cp into T minus T reference, close the brackets, and then this is plus Q. Okay, so what do we have here? The derivative of a constant will be 0, so we will forget about that term. And we have here Cp into T reference minus Cp into T reference. I know this is Cpi, but we said Cp is not changing with time. It's a constant value, so I can cancel out the Cp with T reference with the Cp with the T reference, and I'm left up with the Cp as a common factor into Ti minus T. So the equation will be like that. It will be rho v Cp into dt by dt is equal to rho I Fi Cpi multiplied by Ti minus T plus Q, a very beautiful equation that we're having here. So just to keep dt by dt separately, at last we got dt by dt is equal to rho I Fi Cpi divided by the rho v Cp into Ti minus T plus Q over rho v Cp. And if you look at it, let me just write the Cp in a clear format. We can cancel out those terms here, and my equation is even better. How temperature changes with time is equal to Fi over V into Ti minus T plus Q over rho v Cp. Great, and actually this looks very similar to the D concentration by D time is equal to Fi over V into Can minus Ca plus the rate of reaction. This looks very similar. It's good just to look how similar they are. It just helps in memorizing the equation. So this is the equation. That is the equation that we are obtaining here in a very beautiful format. Very beautiful format. So I'm having one more equation. If you can recall, we had 8 equations. This is like the 9th equation that we have, dt by dt. Well, not to forget, we still have Q. We still have Q to find out. And Q, in this case, where we had our system of a CSTR. Okay, so this is our system, and we had a cooling or a heating process. Considering that the system, for example, it is exothermic reaction, we said that if it's exothermic, what do you need? You need this blue thing, cooling. Of course, why do you need cooling? The whole idea is that when we have reaction, and if it's exothermic, and you say that this reaction, for example, was 50 degrees, it goes up. It goes up because it's exothermic, for example, to 170 degrees centigrade. And that looks like very exothermic. And because it goes up, the conversion is going to be not as required, and it may go in the opposite direction. To bring it down to the optimum temperature, what we need to do? We need to cool to bring it down to the optimum temperature, where we have the optimum temperature to get the maximum conversion. And why do you want to get the maximum conversion? To sell the product of C. Okay, great. So that is the reason in which why you're trying to cool if you have an exothermic reaction. Well, not to think about cooling or heating, it's just a Q term. It could be positive or negative, and that reflects cooling and heating. And in this case, if you think about, okay, I have my coil here. I'll put that in blue because it's cooling. So I have my coil here. So what do I have here? I do have conduction. I do have convection. And actually radiation is nothing to be mentioned here. So I do have conduction and convection. But I would say that even the convection term can be cancelled out. Why? Because the walls of that coil is very thin. It's as if the cool water, the temperature of the cool water is directly in contact with the temperature of the fluid inside the reactor. So in that case, the convection term is going to be cancelled out. Sorry. It's the conduction term will be cancelled out. Why? Because you are saying that if we have the cool fluid here, okay, let me say, yes, that's okay. We have the cold fluid here. My God, I'm messing up the spelling of cold fluid. What's happening? Okay, well, let me draw it like that. So this is the big coil. That is the coil. Okay, so it has a certain thickness. Okay, and what we have inside here is the cold fluid. Okay, so the cold fluid is just flowing in like that, and is going in, and so on. And what do you have around it? Well, what do you have around it is well, I'll take that out. So because it should be something like that, and like around it is some kind of a hot fluid which is being heated. If I just draw that again, so it's something like that. I know it's not that big, I'm just trying to zoom in. So the hot fluid is inside here. So what we're trying to say, there is a convection between the liquid and the solid material, which is the wall of the coil, and there's conduction within the coil itself, where the heat goes through the thickness of the coil, and there's a convection term from the coil to the liquid which is inside the reactor. But we said that because the wall thickness is very small, we cancel that conduction term and it becomes easier, and our Q will simply be represented as a general term. We call it U, which is the overall heat transfer coefficient, but just not to confuse you with the internal energy, which also uses U. So we are going to say that this is the U overall heat transfer coefficient. So this is the U for the heat transfer. Okay, so we have U into A, and again, this is not the A of the cross-section area. This is the A of the contact. So where is the contact? The contact is on this side. The contact is on the walls. This is where there's a contact between this fluid and the other fluid. So here is the contact, and so on. The contact is here. So if you have more contact, you have more heat exchange. So here, this is also a different A. So this is the surface area. So this is the surface area. And this is multiplied by delta T, which is they call it the driving forces, the difference in temperature. So there's more heat in or out depending on the difference in the temperatures. So there's the T here, we've already called it T,
and we were going to call the other T as TC, and it could be named anything. So what do I will say? I will say T minus TC. Now, is it T minus TC or TC minus T? And that's very confusing. If you're talking about the system of the tank, definitely this temperature will be higher. It will be higher. It will be lower if T cool is. It will be lower because of the T cool that is trying to cool up the system, and that means that it should be a negative term. T minus TC should be negative, and because T is greater than TC, so it should be the other way around. I know what I have said was very confusing because it's all about convention, but I try to memorize it in a different way. What I'm trying to say, I'm trying to run this energy balance on the tank, and because I'm doing it on the tank, this is what I write here. I write it as TC minus T. So it is the other system minus my system. So I'm talking about the tank here. I'm doing the balance over the tank. So it is TC, which is the other system, minus my tank that I'm running over, which is T. So this is the way that I do really memorize how to write this equation. So going back, so what do we have here? I think so we already have our equation, which is we already have the equation dt by dt, and this is the term or the equation for the Q, and I will consider that this equation as number 10. Okay, great. So what do we have here? If we're just considering the degree of freedom, so in addition to what we had before, in addition, so the state variables in addition, you're going to have T, temperature, and the normal variable in addition that you're going to have Q, that is coming in within the term, and this is for the V. For the inputs, you're having Ti in additional, and for the parameters, you're having many parameters here. We already counted rho before, but you're having in addition Cp, and you're having in addition the overall heat transfer coefficient and the surface area. And by the way, one of the inputs also is Tc, because we identify the temperature of that cooling water. So that is considered also as an input. If you consider it as a constant or parameter, it's okay. Whatever you want to put Tc here or there, it's not a big deal. The simulation will run similarly. Okay, so it depends actually Tc if you want to use it as a manipulated variable. We don't know what is manipulated variable, but you will use it to control the temperature of the reactor, and in that sense you will put it as an input and not as a parameter. Okay, so just going away from that, so what do we have? We're having two more variables, and how many more equations we have? We have two more equations, number 9 and 10, and this is why we have, instead of 8 minus 8, if you just can recall, the degree of freedom was like 8 minus 8, and now it will be 10 minus 10, which is equal to 0, and to be exactly specified. So that is the problem in which we have obtained an equation for how temperature changes with time. How does temperature changes with time? Now, before I close this, there is some kind of a question that I bring within the exam, which is exactly the same. I don't mean I'll bring it. I mean, I brought it before in some other exams, but instead of having a coil, I'm having a jacket. And this is exactly like wearing a jacket for yourself. I'm having the tank is wearing a jacket. And we have cold water passing through at the bottom of the jacket, and this is how it works, and it goes out. It does not interact with the system. I just want to mention that it does not interact with the system. It does not interact with the fluid directly, in the sense that I'm saying that it's not mixed. They do not mix with each other. What's inside here does not mix with the cold water. So the cold water is cooling, but rather than cooling by coil, it flows through the jacket, and the jacket is a full jacket. It covers the whole body. It covers the whole body. That means it's in front here and also at the back. So it covers the whole the whole body of the system that of the tank that we have here. So what we have cold water getting in, and this getting out is cooling out my system, cooling my system. So what I'm trying to say here is that if you just can recall our the energy balance equation, so it's dT by dt is equal to Fi over V into Tn minus T, and then we said that is plus Q over rho VCP. Okay, so the question here, did anything change in this equation by having a jacket? No, there's nothing had been changed. So what is being changed? What had changed is the Q term, and actually Q term is still the same, which is equal to U A into delta T, Tc minus T. That was the equation. But instead of mentioning dTc by dt, I'm going to mention T jacket by dt. So that is the only thing that is going to change. Instead of saying that this is the coil temperature, it is the jacket temperature, and that's all. That's all in this equation. But the question here comes, like, what is the jacket temperature? We have Tj in and Tj out. It is a good assumption to mention that Tj in is equal to Tj out, because it just enters very quickly here, for example, at a 15 degrees centigrade, and it also leaves at a 15 degrees centigrade. But it will leave, for example, at 16 or 17 degrees centigrade. So it gets hotter, but it gets very quickly in and out. And a good assumption would be that, a good assumption of all that is that we'll call this Tj out, and Tj will be equal to Tj in plus Tj out divided by 2. So that is a good assumption, and it will be very representative of what is the temperature. But just so even to be more specific, talking about model equation, this temperature changes with time. So if we keep this as Tj, we are going to have one more equation for Tj, and we can make use of what we have done before rather than going through the whole part. And this would be Fjn over Vj over Tjn. We are talking about now what is Tjn entering minus Tj out. Okay, so this is like doing an energy balance on the jacket. This is doing the energy balance on the jacket. Okay, so we have Tj in minus Tj out plus Q, and now this is like the Qj, which is different from that Q. It's just the other way around. It's exactly the same, but the other way around, over rho j Vj Cpj. And then we're going to have another equation for Qj, and this Qj is equal to exactly the same, which is U. The overall heat transfer coefficient is the same, and the surface area is the same, multiplied by the T minus Tj. Now it will be just the opposite equation, because we are doing the energy balance on the jacket. So the other system minus my system, which is T minus Tj. So these are the two equations that we can add. And if you look at a moment even more into depth, we have Tj in minus Tj out. If we consider that as equal, which is not, if they are very close to equal, then this Tj is directly equal to what? Is equal to Qj divided by rho j Vj Cpj. But it depends mainly on what is the heat transfer that changes the dTj temperature. So what we are trying to say here, we are adding two more equations. So if I consider that we are adding two more equations, like number 11 and number 12, there's two more equations, and actually we have, because two more variables. What are the two more variables? We have Tj and Qj, and of course we have more inputs. We have Fj and Tj in, and we Tj out all these variables are known values that we do have. Here we just consider that this is in minus out. What about TJ? TJ is like how the temperature of the jacket changing, and here we can assume that what is getting out is very similar. What is getting out here, sorry for that. So if I do this one more, yep. So what I'm trying to say here is that I can remove this out here and saying that it is simply TJ. Why? Because the TJN is like exactly what is leaving the system. It's like what we were talking about previous, the reactions, is that the concentration in the system of a CSTR is exactly what is leaving the system. And it is very similarly represented here. So if you keep it as TJ out, or preferably put as TJ, because we don't want to identify what is TJ out, as if that it is, we don't know what is TJ out. Okay, and this will be like TJ. So these are the equations that we have for how how temperature of the jacket changes. This is in the case if you have jacket temperature. But what I'm trying to say here, using this equation for future uses, if you're going to do some kind of modeling, is good enough to represent the system, and you don't need to add these 11th and 12th equations. So this is how the temperature changes with time. Is a very beautiful equation, and we just can recall you can start from the equation. If you can just recall, you can start from here. You can start from here where we say that dmu by dt is equal to rho n fn hn minus rho f h plus q. Because it's liquid and with delta P is not too large, which is usually the case for most of our for all our CSTR processes, this U becomes H and so on. Of course, we have gas. This U will definitely not become H, it will become H minus PV, and that will be like a different problem that we need to go through if we are dealing with gases. But talking about CSTRs are always for liquids. It's an open tank, and definitely it's for liquids. So if you don't have gases and so on, don't worry about that part. So great, this is what we got, and this is the end of the problems related to CSTRs, where we obtained dH by dt, and we obtained dC by dt, and then we obtained dt by dt. Hope for the best. Thank you very much. This is Dr. Bassam Alhamad, CHENG324 Chemical Engineering. I wish you all the best. Thank you very much.